Good afternoon, everybody. I am Hindrik Kumar, Senior Lecturer, Civil Engineering from Government Polytechnic College, Batala. Today, I will discuss with you on the very important topic of Theodolite surveying from the subject of surveying of 4th semester Civil Engineering of Diploma students. So, Theodolite is one of the most important equipment in the syllabus of Civil Engineering students. So, in the success of every project lies on the proper use of the surveying instruments and mostly the use of theodolite particularly. So, every student must have must possess the knowledge of using how to use a theodolite. So, I hope you will get benefit from my today's lecture. So far we have been measuring horizontal angles by using a compass, that is prismatic compass, with respect to meridian, which is less accurate, and also it is not possible to measure vertical angles with a compass. So, when the objects are at a considerable distance or situated at a considerable elevation or level or depression, it becomes necessary to measure horizontal angles and vertical angles more precisely. So, these measurements are taken by an instrument which is known as a theodolite. So, what is theodolite surveying? I hope you might be remembering, as per the classification of surveying according to use of the instrument. On the basis of use of instrument, we were having the classification of surveying, that is when we use which type of instrument, the same is the classification of surveying. In the similar way, the system of surveying in which the angles, either it is horizontal or vertical angle, they are measured with the help of a theodolite, and distances are measured with the help of a chain or a tape. That surveying is called as theodolite surveying. That is the system of surveying in which the angles are measured with the help of a theodolite. It is called as theodolite surveying, and I have just said that the distances etc., they are measured with the help of a chain or a tape accordingly. So, theodolite is a most accurate surveying instrument, I have just told you, mainly used for. So, a theodolite is used for following purposes. First one is measuring horizontal and vertical angles, locating points on a line. We can locate any point on any line, prolong or produce survey lines. That is, we can prolong any line or we can produce any survey lines with the help of a theodolite. Finding differences of level, that is, we can use a theodolite as a level also. So, when you will study this chapter, you will find it how to use a theodolite as a level. So, we can find out the difference of level between various points with the theodolite also. Next is setting out grades, that is, we can set out various types of gradient, either it is downward or upward. So, we can set out any gradient by using a theodolite. Next is ranging curves. In the subsequent chapters, you will study how a theodolite can be useful for ranging or setting out a curve in the actual world of work. So, a theodolite can also be used as for ranging curves. Next is tachyometric survey. So, you have studied this survey in the classification of survey also. This is a survey in which the distances are not actually measured in the field, but they can be calculated by the use of a tachyometer or a theodolite and taking few readings in the field, and we can calculate arithmetically the distances horizontal or vertical by using this type of instrument which is called as a tachometer, and the survey is called as tachometric survey. So, these are some of the fields in which a theodolite can be used for these purposes. So, on your monitor screen you can find the sectional view of a theodolite instrument, in which vertical axis is shown, objective is shown, telescope and various types of plate, upper plate, lower plate, verniers, lower plate, tri-brach, leveling screws, tripod head is there, tripod legs are there. So, you can see various parts labeled on the sectional view of a theodolite. So, this is very important. You must know all the parts of the instrument which you are using in the field. Next is the detailed view of how vertical axis and upper plate and lower plate they are positioned. This is the sectional view of upper plate and lower plate, how the clamping arrangement is there, how verniers are fitted and how slow motion screw works out. So, this is the detail of the lower plate and upper plate etc. You can see in the sectional view of the details of upper and lower plates. This is quite useful for understanding how the lower plate and upper plate works. It is shown in this sectional view of the detail of upper and lower plates view. This sketch is also useful, in which objective, eyepiece, horizontal axis, vertical axis, horizontal circle, vertical circle, they are shown schematically. So, this sketch is also quite useful for you for understanding various types of circle, that is horizontal circle, by using which we can measure any horizontal angle ranging from 0 degree to 360 degree, and in vertical circle ranging from 0 degree to 90 degree, either it is upward or it is downward, or either it is angle of elevation or depression. So, these sketches are quite useful for understanding the basics of theodolite. So, now we come on to classification of theodolites. How many types of theodolites are there? So, theodolites may be classified as number 1 is transit theodolite, number 2 is non-transit theodolite, and B type classification is vernier theodolites and micrometer theodolites. So, we will study in detail what is a transit theodolite or why a theodolite is called as a transit theodolite. A theodolite is called a transit theodolite when its telescope can be transited, that is it can be rotated, that is revolved through a complete revolution about its horizontal angle in the vertical plane. So, transit theodolite is that when its telescope can be transited, that is rotated or revolved through a complete revolution about its horizontal axis in the vertical plane, whereas in a non-transit type theodolite the same telescope cannot be, please note, when the telescope cannot be transited or rotated or revolved, they are called as non-transit theodolite, in which the telescope we cannot revolve the telescope, rotate the telescope, then it is called as non-transit type theodolite. And these non-transit type of theodolites, they are inferior in utility, that is in use we find them inferior and have now become obsolete, that is they are not used nowadays. So, we find only the use of transit theodolite, which we can rotate or revolve through a complete revolution about its horizontal angle axis in the vertical plane. Next, B type classification, vernier theodolite. So, for reading the graduated circle, graduated mean on which graduations are marked, either it is a horizontal circle or it is a vertical circle. If verniers are used, then the theodolite is called as a vernier theodolite. That is the theodolite in which, for reading the graduated circle, if the verniers are used in that theodolite, the same theodolite is called as a vernier theodolite. Whereas, if a micrometer, that is, it is just sort of an attachment, if that micrometer is provided to read the graduated circle, the same theodolite will be called as a micrometer theodolite. So, out of these two, vernier type theodolites are commonly used. I hope you must have seen these type of instrument in your classes, that is verniers, where the verniers are fitted and how the theodolites are rotated or can be transited in your class. So, these are the type of classifications of the theodolite. So, now we study the size of theodolite, that is, if we are asked to purchase a theodolite, how we can say to the shopkeeper, that is what type of theodolite we want to purchase. So, a theodolite is designated by diameter of the graduated circle on the lower plate. This is very important, please note down. So, if we are to purchase any theodolite, we will have to specify the diameter of the graduated circle on the lower plate. That is, a theodolite is designated by diameter of the graduated circle on the lower plate. The common sizes are 8 centimeters to 12 centimeters diameter of the lower plate, while 14 centimeters to 25 centimeters instruments, they are used for triangulation work. You must be remembering triangulation, that is chain survey, in which triangles are formed for conducting the surveying, that is called as triangulation work. So, common sizes are 8 to 12 centimeters, and for triangulation work it is 14 centimeters to 25 centimeters. So, these are important sizes which we use. Greater accuracy is achieved with larger theodolite. Larger theodolite means large size of the lower plate, as these larger sizes of theodolite have bigger graduated circle with larger division. Bigger size will have definitely the larger divisions, hence used where the survey works require high degree of accuracy. So, please note down, greater accuracy is achieved when the larger theodolite will be having bigger graduated circle with the larger divisions, hence used where the survey work require high degree of accuracy. So, now description of a transit vernier theodolite. Description means what are various parts of a theodolite. So, number 1 is labeling head, number 2 lower circular plate, number 3 upper plate, 4 telescope, 5 vernier scale. We have 4 verniers, A and B on horizontal circle and C and D on vertical circle. So, we have got 4 vernier scales on a theodolite. T frame is there, plumb bob is there for vertical axis, and we also have an tripod stand given with the theodolite box. So, these are the description or the parts of a transit vernier theodolites. These are 8 parts, important parts of a theodolite. So, terms used in manipulating a transit vernier theodolite. So, these are the few definitions or terms which we generally use in theodolite survey. So, first one is centering. So, centering means setting the theodolite exactly over an instrument station, so that its vertical axis lies immediately above the station mark. It can be done, that is centering can be done by means of a plumb bob suspended from a small hook attached to the vertical axis of the theodolite. The center shifting arrangement, if provided, you will see on the bottom of your instrument an arrangement is provided for shifting the centimeter to a few centimeters or few mm without removing the position of the tripod stand. We can move the instrument slightly with the use of a center shifting arrangement. If it is provided with the instrument, helps in easy and rapid performance of the centering. That is, centering can be made very rapidly by the use of a center shifting arrangement if it is provided with the instrument. Second is transiting. Transiting is also known as plunging or reversing. These are two other names given to transiting. So, it is the process of turning the telescope about its horizontal axis through 180 degree in the vertical plane. Please note it. It is the process of turning the telescope about its horizontal angle through 180 degree in the vertical plane, thus bringing it upside down and making it point exactly in the opposite direction. So, it is known as transiting, plunging or reversing. Next is swinging the telescope. You must have seen the in swing and out swing in the case of a cricket. So, similar is the case. It means the turning the telescope about its vertical axis in the horizontal plane. So, a swing is called right or left. Similarly, as in the cricket, it is in swing or out swing. Similarly, a swing is called right or left accordingly as the telescope is rotated clockwise or counterclockwise. Then is face left. If the vertical circle of the instrument where we measure the vertical angles is on the left side of the observer or the person doing survey while taking a reading, this position is called as face left of the instrument, and the observation taken on the horizontal or vertical circle in this position is known as face left observation. Similarly, face right observation, if the vertical circle of the instrument is on the right side of the observer or the person doing the survey while taking a reading, the position of the instrument is called as face right, and the observation taken on the horizontal and vertical circle in this position is known as face right observation of the instrument. Next is the changing face. So, this is an operation. It is the operation of bringing the vertical circle to the right of the observer or the person doing survey if the originally it is to the left and vice versa. That is, if it is left, then we bring it to the right, and if it is on the right, we bring it to the left or vice versa. This is called as changing face of the instrument. It is done in two steps. Firstly, revolve the telescope through 180 degree in vertical plane and then rotate it through 180 degree. Please note down, firstly revolve the telescope through 180 degree in vertical plane and then rotate it through 180 degree in the horizontal plane. That is, first transit the telescope and then swing it through 180 degree. So, these two operations are involved while changing the face of the instrument. Please see on your monitor screen, there is a figure showing the line of collimation. You must have seen this line of collimation in the level chapter of level also in last semester. So, it is also known as the line of sight. Line of collimation is also called as the line of sight. It is an imaginary line joining the intersection of the crosshairs of the diaphragm to the optical center of the object glass and its continuation. Again I repeat, it is the imaginary line joining the intersection of the crosshairs which we find on the diaphragm to the optical center of the object glass and its continuation. This imaginary line is known as line of collimation or line of sight. Again, there is a figure on your monitor screen, that is axis of the telescope. It is also known as imaginary line. This line is also an imaginary line joining the optical center of the object glass to the center of the eyepiece. Please see on your monitor screen, on the left side of the monitor screen there is eyepiece, and on the right side of the screen it is shown as the object glass. If we join the optical center of both the glasses, both the ends, then we find an imaginary line joining these 2 points, which is called as axis of the telescope. Then is axis of level tube. It is also called as bubble line. It is a straight line tangential, please note it, it is tangential to the longitudinal curve of the level tube. You have seen the level tube, which is a curved one. So, this is the straight line tangential to the longitudinal curve of the level tube at the center of the tube. So, this line or axis of the level tube, it is horizontal. When it is horizontal? When the bubble of the level tube is in the center of its run. Again, please note, axis of the level tube will be horizontal when the bubble will be in the center of its run. Again, it is vertical axis. It is the axis about which the telescope can be rotated in the horizontal plane. So, this is an axis about which the telescope can be rotated in the horizontal plane. Next is horizontal axis. It is the axis about which the telescope can be rotated or revolved in the vertical plane. So, these 2 axes are at right angles to each other if the adjustment of the instrument is in the perfect condition. So, vertical axis and horizontal axis, they are at right angles to each other. So, horizontal axis is also known as Trunnion axis. Please note it, horizontal axis, it has got another name, that is Trunnion axis. It is also called as Trunnion axis. So, you have studied both vertical axis and horizontal axis. So, a bubble line or a thread connecting to bubble line represent the vertical axis. So, these 2 axes are, they are at right angles to each other when the instrument is in perfect condition. Now, the adjustment of a theodolite. The adjustments of a theodolite are of 2 kinds. First is permanent adjustments and second is temporary adjustments. So, firstly the permanent adjustments. The permanent adjustments are made to establish the relationship between the fundamental lines of the theodolite and the, if they are once made, that is, if the permanent adjustments are once made, they last for a long time. That is, we do not have to do every time. If it is once made, they last for a long time, and they are essential or necessary for the accuracy of the observations. That is, if the instrument is not in the permanent adjustment, we cannot find accurate results, or for an accurate results or accurate readings, the instrument should be in the perfect condition or its permanent adjustment will be very good. So, permanent adjustment, what is permanent adjustment? The permanent adjustment is the relation of the fundamental lines of the theodolite. So, first is adjustment of horizontal plate levels. The axis of the plate levels must be perpendicular to the vertical axis. First adjustment is the axis of the plate levels, which is a line tangential to the longitudinal curve, must be perpendicular to the vertical axis. Second is collimation adjustment. The line of collimation should coincide with the axis of the telescope and the axis of the objective slide and should be at right angles to the horizontal axis. This is second adjustment. Third one is horizontal axis adjustment. The horizontal axis must be perpendicular to the vertical axis. Fourth adjustment is adjustment of the telescope level or the altitude level plate levels. The axis of the telescope levels or the altitude level must be parallel to the line of collimation. This is the relation between these lines. Fifth is vertical circle index adjustment. The vertical circle vernier must read 0 when the line of collimation is horizontal. So, these are few permanent adjustments. If these adjustments are once made, they last for a very long time. Next, second adjustments are temporary adjustment. The temporary adjustments are made at each setup. Please note down, that is, temporary adjustments are made at every setting up of the instrument. Before we start taking any observations with the instrument, we have to perform the temporary adjustment of the instrument. There are three temporary adjustments of a theodolite. First one is centering, that is, the plumb bob must coincide the center of the instrument station. Leveling, leveling includes the leveling of the tripod stand and also leveling by foot screws. Third is focusing, that is, focusing of first is eyepiece for clear vision of stadia hairs at diaphragm, and second is for focusing for clear vision of the object. So, these are three adjustments which are in the temporary adjustment of the instrument, and these temporary adjustments are to be performed for every setup of the instrument. So, how we measure the horizontal angles? In this lecture, we will study what are various methods of measuring horizontal angles. So, first one is ordinary method, which we use for ordinary purposes. Second is repetition method. This is very important method or accurate method, and which we use only for the accurate work or precise work, used for very important works. The third one is reiteration method, and this method is used when a number of angles are to be observed from single setting of the instrument. So, we will study in detail all these three methods. So, first is ordinary method. So, in the ordinary method, I have already said it is used for ordinary works, that is, where more accuracy is not required, only for ordinary purposes. So, how we do it? To measure horizontal angle AOB as is being shown on your monitor screen in the figure. So, set up the theodolite at instrument station O and level it accurately. Set the vernier A to the 0 or 360 degree of the horizontal circle. Tighten the upper clamp. Loosen the lower clamp. Turn the instrument and direct the telescope towards A, and the reading should be 0 at this time. After bisecting accurately, check the reading must still read 0. If it does not read 0, make it 0. Read the vernier B and record both the readings. That is, we will have to read the vernier B also and record both the readings. Loosen the upper clamp and turn the telescope clockwise until line of sight bisect point B on the right hand side. Then tighten the upper clamp and bisect it accurately by turning its tangent screw or slow motion screw. Read both verniers. Every time we will have to read both the verniers A and B, the reading of the vernier A, which was initially set at 0, gives the value of the angle AOB directly and that of the other vernier by deducting 180 degree, that is it was set on 180